go and turn your textbooks to page 37. Turn your textbooks to page 37. Those in the class did fairly well on their construction quizzes. Hopefully you did well on yours also. Before we get into our material today, I want to do something kind of fun, not tested. We've done this a few times throughout the year. We do something that's not tested. I will say those times are coming to a close. Okay, pretty much from this point forward, we're all boring and miserable, and everything gets tested. But what we're going to do today is not, and we're going to look at some optical illusions. I like these. I like illusions, and I like magic tricks. How many like watching magic tricks? Of course, you understand they're not really magic in most cases. Though sometimes you feel like they are. You know, sometimes you tell yourself, I know this is just an illusion. But I cannot for the life of me figure out how they did that. Are you all familiar with a show called Penn and Teller Fool Us? I love watching Penn and Teller Fool Us. Some of the greatest magicians in the world come to perform in front of two of the greatest magicians in the world. And the two greatest magicians in the world try to figure out how the other great magicians do their great tricks. And if the two great magicians can't figure out how the other magician does it, they have fooled Penn and Teller, the great magic duo. And of course, Penn and Teller like to reveal some of their tricks and how they get done sometimes. And anyway, just cool stuff there. But illusions, where something appears to be one way, and it ain't that way at all. Anyway, I'm not going to go there. So, kind of like how you think the Bucks have this great basketball team, but it's not really
over by Miami.
So I don't feel as bad about my Pacers getting swept by Miami now. But anyway, back to math class here because we are short on time. We got a lot to get in today. But I want you to look, if you would, have your compass at the ready, because we're going to use our compass here in just a moment. Because our compass doesn't lie, but our eyes certainly can. The compass should not lie, but the eye certainly can lie. Looking at picture number 1, there's several different lines, A and B. Without measuring or anything, I just want you to look at the first set of A and B. Which one appears to be longer, A or B? We're on page 37, looking at number 1. Which line appears to be longer? Give it a little check mark next to your longer one. A little check mark next to, unless, of course, you think maybe they're equal. Then don't put a check mark at all. Once you've made your verdict, with your compass, measure A. And then with your compass, measure B. Which one's longer? They are the same. They're equal to each other. Did they appear to be longer? Now, which one looked longer to you, Chris?
I thought they were equal.
You thought they were equal? Okay, so you were correct. They are equal. Anyone think they looked unequal?
Me.
Okay, Ethan, which one did you think was longer?
B.
You thought B was longer? How about you, Genesis? You thought A looked longer. All right, and we're all looking at the same thing. He thinks they look equal. She thinks A looks bigger. He thinks B looks bigger, and they end up being equal. How about the next picture, A and B? Which one appears to be longer? And which one is longer? A. Measure again. Once again, they are equal.
What? Come on.
Which one looks bigger, though?
A.
A looks bigger, doesn't it? But it's not. They're equal.
I didn't get they were equal.
You did not.
Now I want to measure them.
Remember, you're not measuring the arrow portions. You're only measuring the segment itself.
Right.
Which B, the arrows are included with the segment itself. A, they're not.
They're
Look at the next one. Look at the next one. Which one appears to be longer, A or B?
This is so dumb. This is honestly so dumb.
And once again, what's true, class?
They're equal.
But which one appeared to be bigger?
B.
B looks bigger, doesn't it? But it's not. They're exactly the same. Look at the next picture. This one I think is a little easier. Which one's bigger, class?
A.
A, clearly. Go ahead and measure. But you thought B was bigger.
I'm just kidding.
And of course you measure, and of course A is indeed the bigger line.
What?
What? Whoa, wait, no. No,
How?
they're equal again, aren't they?
I don't like this.
So again,
It's an illusion.
It's just like, whoa, but it doesn't look that way, but it is so. The next one is kind of an interesting one. You look at those two segments, AB and CD. Which one's higher on the page, AB or CD?
Wait, what?
On number 2, there's a little line segment AB, and there's a little line segment CD. Which one appears to be higher on the page? Or do they look to be in line with each other? Look to be in line with each other? Take your straight edge and see if they're actually in line with each other.
I thought CD here.
You thought CD was higher? Okay, take your straight edge, see, are they actually in line with each other?
No, they aren't.
No, which one's higher?
CD.
CD is indeed
Of course
higher.
they are.
What?
I said, of course they are.
They are what?
One's higher than the other.
Okay. Look at the next little figure. Do you see how there's three little lines at the top? Label them A, B, C. Label the three little lines at the top, A, B, and C. And the two little lines at the bottom labeled D and E. Do these lines line up with each other?
No.
If so, which lines do D and E line up with? C lines up with which one? E?
No, no. D is with A, and then E is with C.
Use your straight edge. B lines up with D, C lines up with E. But if you look at it from the side, it could throw that perception off just a little bit. So as you look at it from a different angle, it looks different. Of course, the best way is to look at it from dead on like this with your book, and that's a little easier to see. But number three, you see all those little thin lines in figure 1. Then notice there are two thick lines. Look at the two thick lines. Are they straight lines or are they curved?
Straight.
Line up your straight edge with it. See if it's actually a straight line or if it's a curved line. They are straight lines, aren't they? To me, at least, they look curved. And again, different people see things differently. To me, they look curved, but of course they are straight lines. Take a sheet of paper, a thin-ish, cheap sheet of paper, preferably one without reinforced edge. Those tend to be thinner. I want you to trace over the other figure A. See how there's a little figure A in figure 2? Trace over with a piece of paper and see if A and B line up. See if A and B can line up. Do they look like they would line up? So trace over A with your paper and then slide it down and see if you can line up A with B.
Yeah.
To a lot of students though, B looks like it's bigger, looks like it's longer. You look at it again, but they're exactly the same. It's just an illusion that deceives you. Those who remember Chase Williams, he actually had a couple of little, or he had a little red curvy thing, a little yellow curvy thing. You hold them up and they don't look like they would line up, but they do. That's kind of the same kind of illusion here. Number 4, there are 3 airplanes, A, B, and C. Which noses are closer together, is closer to the nose of B? The nose of A or the nose of C? Which one's closer to the nose of B? Call it before you measure. Before you measure.
They're equal.
The nose of A and the nose of C are equal? Okay, go ahead and measure. Measure from B's nose to A's nose, and measure from B's nose to C's nose.
B's nose and C's nose is bigger.
No.
They're equal.
No. They are not equal. Measure again. From the nose of A to the nose of B is much greater
Oh, it is.
than the nose of B to the nose of C.
Wait, what?
I don't like this. This is making my head hurt.
I already have a headache.
Measure from A to B. You'll notice B to C is closer than A to B.
How?
Ah.
How? Not a logical thing.
All right, look at the number 5. Look at the centers of those flowers. Is the center of the first flower the same size as the center of the second flower? Or are the centers different? Is one center bigger? What think you?
The first center is first center is bigger.
First center's bigger, you think they're equal? All right, do the same paper trace thing. Put your light piece of paper over, lightly trace the one flower center, see if you can line it up with the second flower center. Do they line up? Maybe they are equal. But again, on the surface, to some of us, they don't appear to be. Here's the idea. Everyone's eye perceives things a little differently, right? We see things that aren't there. Our eyes can lie to us. Again, that's the whole premise that a magician uses, is if he can make you think you're seeing one thing, and in reality you're just seeing something else, or you're totally not seeing something he doesn't want you to see. And that's kind of the premise here. So wanted to begin with this thought. We just went through a whole bunch of constructions where we constructed perpendiculars. How do we know they're perpendicular? Well, they look perpendicular, sure look like right angles to me. Can you trust your eyes?
No.
No. Well, because you said they were. I could have lied to you.
Did you?
We'll find out.
Come on.
We bisected an angle. Or did you? They sure look like two equal halves. How do you know they're equal?
Measure.
With what?
Ruler.
Certainly not
That's
the ruler.
right.
No, the protractor. That could be printed wrong. How do you know they're equal? How do you know that really bisects? How do you know that angle is really the same size? Now again, logically, it seems to make sense that, yeah, I could see why this procedure would work. But those constructions don't really prove anything, right? Because we could be fallible. With a lot of the things that we tend to observe and see, we say, yeah, that looks like it would be so. Who cares what it looks like? You can't trust your eyes. That's a phrase you're going to hear a lot this year. You can't trust your eyes. Therefore, we must prove everything. Those constructions aren't valid because they look like they work. They're only going to be valid once later on in the year we prove that they're valid. Until then, you're doing them because that's the way I taught them to you, but you're not actually believing it.
Okay.
Because I haven't proven it to you yet. We're going to prove everything in this class that is provable. You say, what do you mean, provable? Well, remember I've mentioned this before. There are certain things that are so fundamental, so foundational, they can't be proven. And that's what forms the basis of our understanding. You have to begin any knowledge with a certain base of knowledge, usually which consists of what individual terms mean, right? I mentioned this before, but one of the big debates in this country is socialism versus capitalism. Well, people don't have the right definitions of those. And if you define something some way that is not accurate, you've now lost all premise of argument, right? You can't argue if you don't understand what something means. Okay, so definitions are important. We've established those. Those are not needing to be proven. Those definitions, they just are what they are. There are other things, though, that you can't necessarily prove. They're just too basic, but they're undisputed, and we'll accept them and agree that they are true. In your terms definitions section of your notebook now, terms definitions section of your notebook now, why don't you get two terms down, which refer to some of these foundational, unprovable, yet undisputed assumptions. One type of statement that we're going to use this year are statements called axioms, or I'll just go singular here, axiom, A-X-I-O-M. This does not mean, hey, are we going to go to the fair tomorrow? I don't know, did you ask Dad yet? No, let's axiom. No, that's not what we're talking about, okay? I mean, to ask a question. Axiom refers to a general statement that is accepted without proof to be true. A general statement that is accepted without proof to be true. A general statement that is accepted without proof to be true. And in any argument, there has to be that sort of thing. For instance, in discussing laws and things of that nature, a law should be that which promotes the good of society, right? Well, what is good? You can't necessarily even completely define good apart from the Bible, right? Our founding fathers tried to use the Bible as their guideline. Of course, that's fallen out of society, but even largely within society that has largely rejected God, there is still a general understanding of, okay, let's all agree this is bad, okay? Now, my argument to them is, why is that bad? I know why I say it's wrong. It's because the Bible says it's wrong, but you're not using that. You know, why would you say it's wrong? But still, society kind of accepts something as okay. We're going to accept that this is fact. We're accept that this is true or not true. An axiom is that sort of thing. Something you can't prove, but we all just agree. Nobody disputes it. Nobody argues it. Not anybody coming out there, no, murder's wonderful. Okay, nobody's necessarily arguing that, though their actions may argue that, I suppose. But, yes.
So could
An
a
ax-
theory be considered as an axiom?
A what?
A theory.
No, very different. A theory is that which must be proven, that which cannot be accepted, that which is not, that which is disputed.
So that's
For
the
instance,
opposite definition for that axiom?
well, that's not necessarily a definition we're going to write down, but very much the opposite. A theory is that which is disputed and therefore must be proven to be established as fact, right? You cannot prove creation true. Nobody was there except God, right? You cannot prove evolution true. No one was there. Now, people will dispute both, though I would argue there's a lot more basis for disputation of evolution than there is creation, but they're still disputed, right? Those are not axioms. Those are not things we would accept without proof to be true. Those are things which would have to be debated or proven true, and then you have to weigh evidence in those cases. But an axiom is something nobody disputes it, we all just accept it's true. There's a similar thing to an axiom, it's called a postulate. A postulate. The biggest difference between an axiom and a postulate, an axiom is just a general statement. An axiom can apply to really anything. A postulate specifically refers to geometric concepts. So a postulate is a geometric assumption accepted without proof to be true. A postulate is a geometric assumption accepted without proof to be true. So postulates are strictly geometric. Axioms can refer to all different areas of life. Axioms can apply outside the realm of geometry. Postulates only refer to geometry. But otherwise, they are, in essence, the same thing. Unprovable statements, but are undisputed statements at the same time. When I say undisputed, by the way, I'm not talking about that, somebody who's just going to be, well, I don't believe that if 2 and 2 give you 4. I don't believe that. Okay, they're being stupid, but like a logical, no well-reasoned disputations, I suppose I should say. So, if you would, turn your books to page 38. Set your notebooks aside and turn your textbooks to page 38. Let's talk through some of these axioms of mathematics that you've already more or less learned, though you may not have thought of them as axioms. Your textbook perhaps used that word, but your teacher may not have or may not have emphasized the word. We're going to emphasize it in this class because we're discussing logical thought. Page 38. You see a table there of various axioms in mathematics. You're going to copy these onto a page in your notebook for homework this evening. For now, I just want to very quickly talk through them. Most of these, you'd be like, oh, I feel like I've heard this before. For instance, axiom 1, nice and loud, Chris.
Quantities that are equal to the same quantity or to equal quantities are equal to each other.
We both have $5. And we both have $5. And y'all both have $5. We're equal, and we're equal, y'all equal. Right? Quantities equal to the same quantity, or equal quantities are equal to each other. Okay? No logical disputation for that. But it's so fundamental, so basic, you can't prove it. We just have to accept it. And again, nobody disputes that if 2 things are equal, and the 2 other things are equal to those same things, that they're all equal to each other. So we'll accept it as fact. Axiom 1. Again, that applies outside the realm of geometry. Axiom 2. Read that for us, Audrey, nice and loud.
If equals are added to equals, the sums are equal. Addition axiom.
Good. We are often going to refer to these axioms by their numbers, but by their names. And this is called the addition axiom. You have equal things. We both got $5. And we both happen to come into possession of 10 more bucks. We both have the same amount. Right? We start with the same amount, we both get the same amount, we both end up with the same amount. Equals added equals, the sums are equal. Again, no one can dispute that, but it's too basic to prove. It's too foundational to prove. Axiom 3, Kendall.
If equals are subtracted from equals, the remainders are equal. Subtraction axiom.
Alright, we both have 3 pencils. We both lose 1 pencil. We still have the same amount of pencils. Duh. Okay? And again, do you recognize, wait, we talked about these already. Where were these in your notebook before class?
In your
The principles section, right? So most of the principles we talked about, we called them principles before. We're now defining our terms a little more specifically as axioms and postulates, but that's really what we're looking at now. Axiom 4, Genesis.
Doubles of equals are equal. In general, if equals are multiplied by equals, the products are equal. Multiplication axiom.
Very good. Again, we talked about that when we talked about it as a principle. You can't dispute it, logically, reasonably at least, and but you can't prove it either. You can demonstrate it over and over again. The truth of these can be demonstrated an infinite number of times, but demonstration does not prove. So, here we go, number 5, very similar, Ethan.
Halves of equals are equal In general, if equals are divided by equals, quotients are equal, the divisor must not be 0. Division.
Good. Okay, so assuming we're not dividing by 0. Now, all of these axioms, by the way, are the premise for, in an equation, what you do to one side, you have to do the other, right? If we had 3x minus 5 is equal to 7, we'd say, well, put a positive 5 here and put a positive 5 here. Why? Because we have equal quantities, and we are adding equal quantities to them. And if equals are added to equals, then what you get is still going to be equal, right? That's the whole premise. Same with subtraction, same with multiplication, same with division, right? All of those are axioms we used in solving equations before. We just didn't necessarily call them axioms, but the same basic premise used there. Number 6, axiom 6, Chris.
The whole is equal to the sum of all its parts.
Good, we referenced this before. Ethan is equal to all of his parts put together. If you were missing a part, like his good eye, then we'd have a real problem. That was Noah. But anyway, you know, then he would be less than he was before. He'd be less, you know, but the whole is equal to the sum of all of its parts, right? Axiom 7, Audrey.
The whole is greater than any of its parts.
Ethan is bigger than his arm. That's a part of him. He as a whole is greater than his part. Again, we talked about all these with principles. Axiom 8 is a new one. This was not one of our principles. Kendall?
A quantity may be substituted for its equal in any process substitution axiom.
Imagine like a clone. You have a, well, he's old, but we'll go with it anyway, a Lebron clone, okay? And LeBron gets tired because he's old and he has to leave the game. But if you have a Lebron clone go in who literally defends the same way, shoots the same way, passes the same way, has the same intellect, exactly the same as LeBron, will you even notice if, other than if he looks a little different, would you even notice if a different LeBron went in if they had the exact same skill set? No, they play the exact same way. You could substitute it in, nothing's lost, right? So a substitution of equals is something we're going to use a lot in this class. This premise of, well, if these two things are exactly the same, they're both equal, then they can be substituted or interchanged with each other with absolutely no loss there. Axiom 9 should sound familiar to you. Genesis?
If the first of the quantities is greater than the second quantity, and the second is greater than the third, then the first is greater than the third.
Again, and another principle we talked about before. If Ethan's taller than Genesis, and Genesis is taller than Audrey, then Ethan's taller than Audrey. You're welcome, Kendall. You're my favorite. Questions on those? Questions on those? All right. Postulates on the next page. We're going to copy these on a separate page. So in our axioms and postulates section of your notebook, you're going to have a page of the axioms. The next page is going to be postulates. We're going to copy those down for homework also. Let's go and look at postulate 1 for now. Ethan.
For 2 given points, one and only one straight line can be drawn.
This doesn't apply outside the realm of geometry, right? You can't make this apply to money or to height or to... It only applies to geometry, which is why it's a postulate, not an axiom. Again, we just generally call them principles before in our discussion, calling them postulates here. But through 2 given points, you can only draw one straight line between them. You can retrace the straight line as many times as you want, but there's still only the one straight line that goes between them. Anything else would have to be a curve or a broken line. Can you prove that? No. But you can demonstrate it over and over again, and no one reasonably disputes it. Postulate 2, Chris.
A straight line is the shortest line that can be drawn between 2 points.
You can draw a whole lot of lines, curves, broken lines, etc., but the shortest line between these two is going to be the straight line. Again, no one reasonably disputes that, right? Postulate 3, Audrey.
Straight line may be extended indefinitely, or it may be limited at any point.
The thought behind this is a line is technically of infinite length anyway, because it's the intersection of 2 infinite planes. So a line, meaning line segment, could be extended because it's already infinite A. We already just took a limited portion. You're just extending the limits a little bit, right? Or you could limit it further at any point. So a line is infinite. You can extend the line, limit a line at any point along that technically infinite line. Postulate 4, this is kind of a fun one. Kendall?
A circle or part of one may be drawn about any point as the center and with any given radius.
This is basically saying if you have any plane, because a circle is a plane figure, if you have any plane, any flat surface, and you have a compass, you can put the point of the compass anywhere. You can open it any amount and make a circle there. Duh, right? So, all right, well, pick up your compass and no, don't put it there. You can't put it right there. Why not? You just can't. No, you put a circular part of one may be drawn about any point of center, any given radius. Basically, you put a circle anywhere you want. And postulate 5 is an interesting one here, Genesis.
A geometric figure may be freely moved in space without any change in form or size.
Change the word in to through, maybe freely moved through space. That's the way I'm going to phrase it in this class. This is mind-blowing, I know. See this triangle? Look at it, kind of get a mental picture of how big it is. Now watch. Did it get bigger or smaller? Same size. Okay, if I move a figure through space, it doesn't change how big it is. It didn't change what it looks like. It looks the exact same, even though I moved it. Okay? This, by the way, this postulate defines what we call Euclidean geometry, which is the branch of geometry we study in this class, based on the works of Euclid. Have we talked about Euclid yet? We're going to get to him later. He took the time in 13 different books called the Elements of Geometry. He put together line by line all the geometric truths that he observed. Now, 5 of his books, the first 5, deal with plane geometry. That's what we're studying in this class, so the first 5 books of Euclid kind of compiled into one text and simplified a little bit for high school. But thousands of years ago, he went line by line proving every detail about geometry. This is one of the things that opened the door to his discoveries, was this understanding that as you move a figure through space, nothing happens to it. It maintains its size. So anyway, unless of course it's like a priceless vase, but this is postulate, it's priceless geometry. For priceless vase, you might drop it, and then there's a change in form or size. In geometry though, a figure may be moved. This postulate really defines Euclidean geometry. With these different axioms, postulates, again, none of them can you prove. Can you prove to me that that triangle over there didn't change as I moved it? No, but you're being stupid, Mr. Nadaski. You wouldn't say that, hopefully, but yeah, I mean, no, of course you can't prove it, but we all accept, we understand that it's true, right? And here's the key. If we will accept these 14 basic truths, there are a bunch of other things that then must be true based on these things and certain definitions we've discussed. Certain facts we can prove. Certain, not theories, but we'll call them theorems, that will prove about different geometric figures based off of this foundation of unprovable content. So I want you to, yes sir?
How can you prove something, if you're using an unproven concept to prove it?
If no one disputes the concept, if we accept that this concept must be true, because it's demonstratable, though unprovable, if it's undisputed, then we'll accept it, but you have to start somewhere.
So does that mean that the other things that we will decide are true, does that mean they're technically unproven as well?
No, they are proven because we accepted that this must be true. Any discussion must begin somewhere, right? Any discussion has to have a certain baseline. And again, this is the argument for the existence of God. Well, if you have to start somewhere, where did anything start? How do we have any knowledge at all? How can we know anything? See, the agnostic claims we can't know anything because knowledge is all relative. There has to be some absolute truth. God defines that absolute truth. We have a basis for all argument in our lives. Again, an agnostic doesn't. But you have to begin somewhere, right? You have to be able to accept, you have to establish some common ground in some conversation. Again, this is one reason why in politics things are so divisive. The right and the left will not agree that either party has any merit whatsoever. 10 years ago, people could agree, okay, I don't like everything this guy says, but he's right about this. And now both sides absolutely refuse to acknowledge any merit on either side. There's absolutely no common ground now, which is why the discussion's breaking down. You have to establish some commonality. And our commonality is we can all agree, unless you choose to try to dispute one of these, in which case you'd have to prove one of them wrong. But unless you could dispute one of these, we're going to assume they're true, in which case that forms the basis of logical argument. And from the basis, now you prove things out of that. For instance, in our Christian faith, there is one foundational axiom that if this one statement is true, everything in our Christian faith holds up. If this one thing were not true, everything falls apart, but you can't prove it. So, what do you think? What would be the fundamental axiom of our Christian faith?
God.
What about God?
That God is real.
Okay, if you accept this axiom I'm thinking of, then God is real. I can prove it to you. But you'd have to accept this axiom first. Someone else? Let's see if we can get some other help before we come back to you. Get the other people involved. I want you to think. What if I could prove this? Everything would hold together, but I can't prove it. We just have to accept it.
The existence of creation.
If this one thing is true, creation happened. I can prove it to you. What about it? If we can prove this one thing true, if we accept this one thing is true, I can prove to you the Bible is the Word of God. All right, Kendall, Audrey, it's your turn. All the older kids have spoken. Time for the 10th graders. They've all been wrong so far, so it's no shame if you're wrong. If we accept this one thing is true, I can prove to you God is the only living God. All right, your turn, and we'll come back to Chris. He's tried to put his hand up a couple times.
The tribulation period?
I wouldn't describe that as foundational, but if we accept this one thing is true, I can prove to you the tribulation's coming.
Faith?
What about faith?
If we prove that faith is real, like, or if we prove that, well, yeah, God, I mean, God's the only thing that I can think of that would prove that everything is real.
No, you already said that one.
What is the answer?
I want you guys to get it. I don't like giving you stuff. I like you guys to get stuff. That's the whole point of this class, make you think. What? A hint. Genesis was the closest.
Oh, if we believe that the Word of God is the real words of God, that God gave the exact words.
If you accept this one thing is true, I can prove that God gave the exact words. Ethan?
Give me a headache, just like I think about eternity. It gives me a headache every time.
I can prove that Jesus came to this earth and was the Son of God. I can prove he died on a cross. I can prove he rose again. But you have to accept this one thing is true, and I can't prove this one thing. I can prove there's a heaven and a hell if you accept this one thing.
The Bible.
What about the Bible? That's what she said. She said the Bible. What about the Bible?
That the words are true.
That the Bible's true. You can't prove that the Bible's true. But no one's ever been able to prove it false. They've tried. People have tried to prove the Bible false. No one's been able to do it. If we accept that the Bible is true, we can't prove that it's true. We can demonstrate over and over again. See, the Bible was right. The Bible was right. The Bible was right. The Bible was right. But that doesn't prove that it's right. You can't prove that the Bible's true. But you can't prove it false. People have tried to dispute it. They've been wrong every time. If we accept that the Bible is true, everything falls into place because everything we believe rests upon the Word of God. Now, we can demonstrate that it's true. This is the reason why in Bible Doctrines, the very first chapter you're studying is bibliology. Let's study the Bible, about the Bible, how it came to us, so we can show, it doesn't prove, but show that it's reliable. And once you accept the Bible's reliable, yes, we can all agree, although it's not been proven, the Bible has to be true. It's supernatural preservation. Unbelievable how it's been preserved throughout time. Unbelievable how it's been preserved word for word throughout thousands of years. Okay, that's incredible. The fact that there have been so many attacks against it and yet it survived, okay, that shows it's significant. But it's not until you agree, okay, I'm going to accept that the Bible is true. Whatever it says must be true. Well, now it's the Word of God because it claims to be. Now God exists because he claims in the very first words, in the beginning, God, assuming the existence of God. But that's proven if you accept that the Bible is true, then there must be a God. If you assume that the Bible is true, tribulation's happening. If you assume that the Bible is true, I'm trying to remember yours, that he is the only living God, because in the Word of God it says he's the only living God, right? So if you accept that the Bible's true, everything's solid. So you understand the only thing you would have to do to convince me not to be a Christian is prove that the Bible's wrong. Even once. Just one place. Show me where the Bible's wrong. And my whole faith crumbles. But if not, and no one's been able to do it, although humans have attacked it since its inception, then I hold to the fact I'm going to accept that the Bible is true even though I can't prove that it is. Again, I can demonstrate time and again that it is. But if you can't prove that it's wrong, I'm going to accept it as true, and then from there, I can prove all kinds of things, right? That's kind of what we're doing with geometry. We're going to accept these axioms and postulates we just read through. We're going to accept them as true because no one can prove that they're not. And from there, we're going to prove a whole lot of things. Some of the things we're going to prove are what we call informal statements. So continue looking here. You don't have to write this term in your notes. Informal statements. These are statements that the proofs hinge directly. An informal statement, its proof hinges directly on these axioms and postulates. Very short, very easy things to prove. That said, your first informal statement, we never proved. The rest of the informal statements we will. So tell you what, real quick, while we're thinking about it, take out your notebook and turn to the informal statements page. Turn your notebook to that informal statements page. What I want you to do is draw a line under informal statement 1. Just to kind of set it off from all the others, because informal statement 1 was not proven. We're going to use axioms, postulates, and definitions to prove these other informal statements.
So draw and write not.
Yep. We're just draw a line under it just to kind of offset. If you want to write off to the side, not proven, you can do that if you want. All right, we're not going to take time to write these. We're just going to talk them through for now. Look at informal statement 2. Ethan, you're up. Go ahead and read that informal statement for us, sir.
Two straight lines can intersect at only one point.
Now, this was one of our principles, but it's not a postulate because I can prove this true based on other acceptances. Okay, prove that two straight lines can intersect at only one point. Well, if they didn't intersect at only one point, then somehow, some way, they'd have to intersect a second time. And you might say, well, Mr. Heskey, that's ridiculous. Those are curved lines. Those aren't straight lines. How do you know? Well, they don't look straight. Can you trust your eyes?
No.
No. Okay, so they're straight lines, even though you don't think they are. They are. They're straight lines, and they intersect twice. Well, wait a second. Look at postulate 1. We accepted postulate 1 as true, remember? Through two given points, one and only one straight line can be drawn. Oh, then apparently those can't be straight lines, both of them. So apparently two straight lines can't intersect at more than one point. Do you see how a postulate is used to prove the informal statement? In postulate 1, we had to accept. We couldn't prove that. But once we accept it, it does prove the informal statement. Do you see the difference between acceptance and proving? Look at informal statement 3, Chris.
A line can be divided into two equal parts only by only one point.
All right, so here's the thought. There's only one point that can divide a line segment into two equal parts. We call that point, class, the midpoint. Okay, so let's call this midpoint here, let's call it the point P. You say there's only one, huh? I say there's two. This is also a midpoint. So, if that were true, if it were true that there were two midpoints, that means, of course, that AP and BP would have to be equal, correct? It also means that AP prime and BP prime would have to be equal, right? Because if it's a midpoint, if it divides into two equal pieces, then AP and BP are equal, and AP prime and BP prime are equal, right? Because they're both midpoints. All right, well, that also means that since AP and BP are equal, and we know that the whole is equal to the sum of all of its parts, we've accepted that to be true, then AB must equal AP plus BP, correct? Because BP and AP are two parts of AB. But since AP and BP are equal, then we could say that AB is equal to AP plus AP, correct? Or in other words, AB is equal to 2 APs. Agreed? And if equals are divided by equals, or you could say halves of equals are equal, then this means that AP is half of AB. Correct? Again, all of this is stuff that we can prove. This is based on assumptions we've already accepted. Now then, we could do the same thing for AP prime and BP prime as we just did there, right? If we just put primes on all of that, we could eventually say that AP prime is equal to half of AB, correct? Which means if quantities are equal to the same quantity, they're equal to each other. Or you could say halves of equals are equal. Well, AP and AP prime are both half of AB. So therefore, AP must equal AP prime. This segment right here and this segment right here are the exact same length. The only way that two line segments can be equal, based on a definition, is if their endpoints can be made to coincide. Well, A already coincides with A. So apparently the only way this could be true is if P and P prime actually coincide at the same point, in which case you now have only one point that can divide a line into two equal segments. Do you see how we can prove that that's true based on some definitions and axioms and postulates? Do you start to understand what proving means? It's taking things that have been accepted and showing, well, if that's true and that's true and that's true, then this has to be true also. That's proving something. Very similar proof would be used on Informal Statement 4, but doing with angles. Audrey, read Informal Statement 4 for us.
Given angle can be divided into two equal parts by only one line.
It's basically the same proof again, where you would say, well, you say only one line can bisect the angle? No, I say there's two. But in proving, you would have to prove that this is half of the angle and that this is half of the angle, which means these two halves are equal since they're halves of equals. In which case, definition of equal angles, their sides can be made to coincide, so these two sides would actually have to coincide, in which case it really is just the same one line at this point. You can't really have two. The two lines would have to coincide, so there is only one line that can divide an angle into two equal parts. Questions on that? Informal Statement 5. Genesis.
All straight angles
All straight angles are
are equal.
equal. Well, here's the thought. What is a straight angle? It's an angle whose sides form one straight line. Straight angle, an angle whose sides form one straight line. Make sure you're just keeping up with your studying, terms and definitions. You can't forget that stuff. Well, all straight lines have the exact same shape, right? All straight lines can be made to coincide. What a straight line is, the intersection of two planes, so all lines can coincide. And if angles are equal, if their sides can be made to coincide, and all straight angles, sides form one straight line, then all straight angles have to be equal, right? So there's Informal Statement 5. Informal Statement 6, Genesis.
All right angles are equal.
Right angles are defined two ways. One of the two ways is the angle formed when two straight lines meet to form equal adjacent angles. The other definition is half of a straight angle. Well, if all straight angles are equal, and right angles are halves of straight angles, and halves of equals are equal, then all right angles have to be equal. Agreed? Okay, so that must be true. Again, that can be proven based on previous assumptions like halves of equals are equal. Informal Statement 7, Ethan.
Only one perpendicular can be drawn to a line at a point in the line.
Now this one's interesting because this kind of ties into that construction we did, right? Remember we did the construction where we had a line, and I picked a point, we said we're going to put a perpendicular at that point. Well, let's suppose Kendall on her construction quiz drew that line, and she said, that's my perpendicular. And I came along with the red pen, and I said, no, Kendall, that's the perpendicular. She says, mine's perpendicular also. Well, this informal statement says you can only have one perpendicular. Well, if you had two perpendiculars, hypothetically, Ethan, you're not writing these down right now, just listening, just watching, you shouldn't be writing anything. If you had two perpendiculars with two different lines, you have 1, 2, 3, 4 different line segments, correct? Forming 1, 2, 3 different angles. If Kendall had a perpendicular, then this angle right here would be a right angle. And if my line's perpendicular also, then I also have a right angle. What do we know about all right angles?
That would be 90 degrees.
No, they're all equal. We don't define things in terms of degrees because that's a measurement which could be flawed. But we know all right angles are equal. We just proved that in Informal Statement 6. If all right angles are equal, then what has to be true about my angle and her angle? They have to be equal. And equal angles are defined as angles whose sides can be made to coincide. If my line does not coincide with her line, they are not equal. In which case, we cannot both have right angles. The only way would be if our two lines actually coincided. Which would mean if my red line came down on top of yours, Kendall, then we both have perpendiculars. Otherwise, you don't. Anyway, so no, you can't have two different perpendiculars. Well, mine's perpendicular also. No, there's only one perpendicular. Because to have more than one would be to violate the other things we've already agreed had to be true. Questions on that? Look at informal statement 8, kind of building on this thought genesis.
Complements of equal angles or of the same angle are equal.
Complements of the same angle or of equal angles are equal. Let's suppose we have this angle. We'll call it angle 1. The complement of angle 1 is that which completes a right angle, correct? So you say, that doesn't look like a right angle. You don't trust your eyes, that's a right angle. That's a right angle. So that means angle 2 is the complement of angle 1, correct? Well, if I drew a line like this, I can also make a right angle down here, which would make angle 3 the complement of angle 1. We know that if they are complements, by definition, complementary angles class, two angles whose sum is a right angle. Make sure you know your definitions. Two angles whose sum is a right angle. So if angle 1 and angle 2 are complementary, and if angle 1 and angle 3 are complementary, that is, that 2 and 3 are both complements of the same angle, then that means that angle 1 plus angle 2 must equal a right angle, and angle 1 plus angle 3 must equal a right angle. Definition of complementary angles, right? And we said that all right angles are equal. Well, if that's a right angle, and if that's a right angle, and all right angles are equal, then angle 1 plus angle 2 must equal angle 1 plus angle 3, because they're both right angles, correct? This sum is a right angle, that sum is a right angle, the two sums must be equal. But if I were to take equal quantities and subtract them from equal quantities, the remainders must be equal. We accepted that subtraction axiom is true. That means that the complements must be equal. Make sense? Questions on that? Very similar thing on informal statement 9, Ethan.
Supplements of equal angles are, or of the same angles are equal.
Good. Supplements of equal angles or of the same angle are equal. Again, basically the same premise, except instead of finishing a right angle, you would finish a straight angle. So you would say supplementary, right? And what do we know about supplementary angles, class? Two angles whose sum is a straight angle. But what do we know about all straight angles? They're all equal. Same proof, okay? Just doing with straight angles instead of right angles. Questions on those informal statements? We're out of time, but that's where we'll stop today. Any questions on those? All right. Tonight, for homework, you're going to copy these into your notebook. So homework is to do pages 38 to 42. Pages 38 to 42. Copy your axioms, postulates, and informal statements. Pages 38 to 42. Copy your axioms, postulates, and informal statements. Very quickly, want to make sure you know exactly what I expect. Your informal statements you're going to continue to have on one page, but you're going to have a line under informal statement 1. You all should have already written that line there. You're just going to finish out the informal statements down through number 9. Okay, we'll get to more the informal statements, you do all of them. Just finish those out. Axioms, they get their own page. At the top of the page should say axioms. And you'll copy your 9 axioms. There's more coming later, but for now, 9 axioms. On a separate page, behind it, postulates, and copy those first 5 postulates. Everyone understand what's expected on the homework? Yes, ma'am.
All informal?
Yeah, go and get all of them, because we're going to finish talking about the rest of them tomorrow, and that just saves you homework over the weekend. So there's only, if we talked about the first 9, there's only 5 more. So let's go and get them all copied down. Again, use shorthand, okay? When it says right angle, root angle symbol, right? So use shorthand. It should not take you as long to write as it is to type out in the book. All right, you are dismissed. Have a wonderful rest of your day.